Hi class, we are on the next section, chapter 1.4. Today we are going to talk about rational expressions. If you remember what the rational numbers are, those are when you have an integer over another integer, also known as fractions. So if we're talking about rational expressions, we're going to be talking about algebraic expressions that come in a rational form. Or, in other words, a fraction that has a polynomial over another polynomial. So we'll talk about how to do arithmetic on those, how to add, subtract, multiply, divide, that sort of thing, how to simplify, and some of those questions. So again, this is a review from an Algebra 2 class. We'll go semi-deep into this like we have in the last section, but again, this material is meant as a sort of review. So let's go ahead and get started. So again, a rational expression is an expression of the form a over b, where a and b are themselves algebraic expressions, which we covered in 1.3. b is not allowed to be 0, right? We're not allowed to divide by 0, okay? So the domain of a rational expression is anything that you can plug in to either the expression a or the expression b, as long as it does not make the expression b equal to 0. So anything you can plug in except for the things that equal 0 in the denominator, okay? So we express this domain in set-builder notation as all real numbers, such that this expression b here does not equal to 0, okay? So when we're simplifying rational expressions, we always want to factor everything first, okay? So, which is good because that's what we talked about in the last section. So whenever you run across a rational expression, so polynomials in the numerator or denominator, just fraction everything. If you have no other idea of how to get started with the problem that you have before you, just factor everything, right? And then something will show up and be like, oh, okay, now I understand I can start to do X, Y, or Z, right? So the way that we do arithmetic on a rational expression is the exact same way we do arithmetic on regular rational numbers, okay? Because a rational expression is just a rational number. If I have a polynomial in the numerator and a polynomial in the denominator, and I say let x be this specific number, I then can simplify my numerator into a single value and my denominator into a single value, and all I have is a single value, a rational value, a fraction. So always think of your algebraic expressions as being a number. It's just that your number has some strange form, okay? That'll help you get through the algebra that you need a lot easier. So it'll be just like doing arithmetic on regular numbers. The only difference is that your regular numbers have a different form, and then sometimes they have their own rules, like factoring, right? The way you factor a number, 10 for instance, is you look at what multiplies to 10, 2 times 5. When you factor a polynomial, there's a little bit more work that goes into it, but it still works out the exact same way, okay? So in order to make common denominators, which is very important when we're talking about fractions, right? We build our LCM, our lowest common multiple, one factor at a time from all the denominators that are present, okay? So we build our lowest common multiple out of the denominators that are already present. So we're going to build this by looking at the factors that are in our denominators. This is the same way that we would do it if we had a regular rational number. Okay, so let's go ahead and look at our first example. Okay, so we want to find the LCM for each set of algebraic expressions. This is really just practice for building the common denominator for anything that might show up, right? So for instance, let's say I had 1 over 4x squared plus 1 over 2xy, and I needed to make a common denominator. Well, I need to find the LCM or common denominator for those two denominators, okay? So we're assuming that these are two denominators from two separate rational expressions. So the way that we do this is we build it one at a time, okay? I take my 4x squared, for instance, and I look at it in terms of its factorization, right? 4 is 2 times 2, x squared is x times x. So really, if I were to expand this out, it would be 2 times 2 times x times x. When I look at my next term, I just need to take the things that are missing. So if this is 2xx, I already have a 2, I already have an x. I can already make this number out of this number. The only thing that's missing would be a y. Okay? So we're going to take any one of these and use it as a base. We can use the first one or the second one. In this case, I took the first one, my 4x squared. And we're going to look at our expression and only use the pieces that are not already in our current base. This is my current base, okay? My current LCM that I'm using to create a base for the LCM. This is what I have. I'm going to then look at the next number and say, what am I missing from here that I can add into this one so that my LCM can generate both of these numbers independently, okay? The expression 2xy, it only adds a y to our base since we already have a factor of 2 and a factor of x, okay? Because 4x squared has a 2, an x, and an x. So this 2 is not necessary. It doesn't add any more information, and this x does not add any information. But I don't have a y in my 4x squared. So, again here, 4x squared is 2xx. So note that I already have the 2x present that I would need to make a 2xy, but I don't have the y. So my LCM would be my 4x squared, and then I just throw in the missing piece here, which is the y. So if I were to expand 4x squared y, I would have 2xxy. I can make a 2xy out of that very easily by grabbing 1, 2, 1x, 1y. Or I can make my 4x squared because I have the 2 times 2, my x, and an x. So my 4x squared y can generate my 4x squared, and it can generate my 2xy as well. Okay, so that's how we're going to build this out. And that's exactly how we do this when we factor regular numbers. If I say find the factors of 100, you would break it down to its prime factors. Okay, if I wanted the LCM of 8 and 9, I would break 8 down to its prime factors, 2 times 2 times 2, 9 to its prime factors, which is 3 and 3, and that would be what it is, right? So 2 times 2 times 2 times 3 times 3 is basically 8 times 9. It would be 72. Okay. So same thing here. I have 3 different terms that I want to break down. Okay. Go ahead and pause right now and try to figure this out for yourself. What would be that LCM? I'll give you guys a second to pause it. Okay. Hopefully you try this on your own. So let's see what we have. So I'm going to take all of one of these. It doesn't matter which one. I just need to take one of these to start with my base. You can start with the biggest one, right? This one has a lot of stuff going on, or you can just take the first one. It doesn't really matter, okay? So we're just going to start with the first one, 10x y squared z. I'm going to come into my next term and say, what am I missing from what I have already? Well, I have a 10 and a 5. So what would I need in order to do this full time? So 10 is 2 times 5. 15 is 3 times 5. They both already have a 5, but this one doesn't have a 3 in it. So I would add in a 3. Okay. I have one x here, but this has 2 x's. So since I already have one, I would just take the extra one that I'm missing, right? This has one z. Well, let's look at the y's. This has 2 y's. This has only 1. I have more than enough y's already in my 10x y squared z. Okay. If I'm looking at the z squared, this has 2 z's. I already have 1, so I'm missing 1. So I take that extra z. So this term, 15x squared y z squared, will contribute to the base I have already, a 3, an x, and a z, right? So I have 2, 5, and then this adds a 3. I am being contributed an extra x. Here I have more than enough y's, so I don't need this y. Here I need one more z so that my powers match up. So I got the 3, the x, and the z. Okay. So far now I have 30 x squared y squared z squared. So that's my current LCM. So I need to come in and add to that again what I have from 4xy z cubed. Now, 10 is 2 and 5. 15 was 3 and 5. So the only thing that got added from here that I was missing was a 3. The next term is 2 times 2. 30 is missing, only has 1 2 if I break this down, right? It's 5 times 6, or if you break that down, that's 2 times 3 times 5, right? 2, 3, and 5. 4 has 2 2's in it. So I'm missing an extra 2, so I'm going to steal that extra 2. That'll make this 60, okay? I have 2 x's here. This only has 1. I don't need any x's. This, my current LCM has 2 y's. This only has 1. I don't need it, right? This has 2 z's, but this has 3. So I'm going to take 1 from it. So the only thing that this adds is a 2 and a z that I'm missing from all of the other pieces, okay? So my current LCM is 60 x squared y squared c cubed. Now, I want you to think about this a little bit, okay? So that's how we think about it, but there's a faster way of doing this, especially when it's not a polynomial. If it's just a monomial, right? This is 3 monomials. This is only one term, one term, one term. The easiest thing to do is to take your 10, your 15, and your 4 and figure out what your LCM would be for 10, 15, and 4. There's actually an easy way for it to do this with the numbers. This is the way that I tell my students to find a common denominator when it's just numbers and no x's and y's and stuff. Find the highest number you have of all the ones that you have. So in this case we have 3, we have 10, 15, and 4. I take my 15 and I just count multiples of 15 until all of the other numbers go into it. And whatever number I have, that's the one that works. So for instance, I'll start with 15. 10 does not go into 15 evenly. 4 does not go into 15 evenly. So I have to count another multiple. So my next multiple is 30, right? So I know you can't see me, but I'm holding up 2 fingers right now because I went 15 and then 30. That's the second multiple. 10 goes into 30 evenly, but 4 does not. So then the next multiple is 45. So that's the third multiple. 10 does not go into 45 evenly. 4 does not go into 45 evenly, right? So then the next multiple is 60. 10 goes into 60 evenly, and 4 goes into 60 evenly because 4 times 15 is 60. So that's how I figure out for my numbers. That's my LCM for the numbers. For the exponents here on x, y, and z, let's see about what we notice. Okay, here I have an x squared. This is an x, this is an x, this is an x squared. The highest power that shows up is the one that I use. This is a y squared, this is just a y, this is just a y. I'm going to use a y squared. This is just a z, this is a z squared, but this is a z cubed. I use the highest exponent that shows up. So it's actually fairly easy to find the LCM of 3 or 4 or 5 monomials. You just use the highest power that you have for your variables, and then you count multiples of your highest coefficient. Okay. Now when we have something like this, this is a little bit different. Okay. When we have 3 polynomials, we want to utilize the method that I've been showing you through A and B already, which is taking one and looking at its factors and building it up piece by piece. Okay, so let's start with the first one. We're going to factor each of these. X squared minus 1, this is a difference of squares. So that's going to give me x plus 1, x minus 1. Okay, this is x squared plus 2x minus 3. It's a trinomial. It's monic. So I just look at factors of 3 that add or subtract to a positive 2. One of them needs to be negative though, so that when I multiply I have a negative number. It's actually very easy. A positive 3 and a negative 1 will work for us. Okay. Same thing here. It's a trinomial. It's monic. I need factors of 3 that add or subtract to 4, and I need both of those numbers to be positives or both negative, so that when I multiply them I get a positive out. So here this is also very easy. This is going to be x plus 3, x plus 1. Okay. So now that I have the factored form, okay, just like here, I had factored this to its pieces, I'm going to build my LCM one at a time. I'll just take the first one, x plus 1, x minus 1, and that's where I'll start. Okay, I have the whole thing already. Okay. Next, I look at the next term, x plus 3x minus 1, and I say, what do I have and what am I missing? Well, if this is what I started with, I already have an x minus 1 term, but I don't have an x plus 3 term. And then when I come to my third part, I now have an x plus 3 because I grabbed one from here, and I already have an x plus 1 because I had it from the initial point. So again, if you look at this is my x squared minus 1, right? That's the x plus 1, x minus 1. I can make that here. The next one, x plus 3, x minus 1, I can make with these two terms. And my last part, x plus 3, x plus 1, I can make with the two outer terms. Okay, so let's look at an example. Say that I want to simplify the following. Okay, so again, this is a review, so we're going to jump right into a problem where we're using everything. We're going to talk about how to subtract rational expressions, how to add rational expressions, and how to simplify and how to multiply rational expressions. The only thing I don't have in here is division. Okay, but division is the same thing, right? You take your second term and you multiply times the reciprocal of it. So everything that we're going to do here is just the same way that we do it when we add, subtract, multiply, divide fractions. There's nothing different. The only difference is that the things in the numerator and denominator are algebraic in form. Okay, they're polynomials. Now, you might be saying, I'm going to take this number and I'm going to distribute it to all three, and then I'll add them, subtract them together, and what have you. I'm sorry, but that's a terrible idea, because you then have to I mean, you can. I'm not gonna knock you. You can do that, but it's probably not the best idea to do that. Number one thing we're gonna do, factor everything that we can. Okay. After we factor everything that we can, we make our common denominators and we simplify the inside. And then we can just talk about multiplying stuff, because multiplying fractions is easy because we get to cancel everything. I love multiplying fractions. That's the easiest thing to do. Adding, subtracting sucks because you got to make common denominators. So I just practice till it's easy, right? So let's go ahead and factor all of the things. Okay. Voila, abracadabra. This is the factored form of everything. Okay. Here we have a 3 and a 2 can add to 5. Here we did this earlier, right? We know that this is x plus 3, x minus 1. So that was nice. That's just me being lazy. Here, if you factor out a 3, you have 3 times x squared plus x minus 2. And then that factors very easily to x plus 2, x minus 1. And then here, if you try to do this on your own before I showed you the next slide here that I did, maybe you were racking your head and you couldn't figure it out. And that's because it's not factorable over the integers. Okay. So this one we can't do anything with. We have to keep it as is. The next thing I want to do is I want to build an LCM. The nice thing about it being factored, okay, just like this, is it's very easy for us to figure out what we need. So here what we're going to do is label all the things that we have. I have an x plus 2, I have an x plus 3, and an x minus 1. Those are the only things that show up in the denominator here. So that's going to be my LCM. X plus 3 times x plus 2 times x minus 1. Now, when I do this, I can do it all at once. I'm not sure if I did or not, because I made this thing a long time ago before I made these videos. But when I add all these together, it will all be over one denominator, which is that LCM. X plus 3, x plus 2 times x minus 1. Here, I just need what's missing, right? So this top and bottom, I'll multiply times x plus 3, x minus 1. Here, top and bottom, I'm missing only x minus 1. Here, top and bottom, I'm only missing x plus 2. So I can go from this form straight to the next line. I could skip about 3 steps, right? If you do it correctly. My denominator would be x plus 3, x plus 2, x minus 1. My numerator will be 4 times x plus 3, x minus 1 minus 3x times x minus 1 plus 1 times x plus 2. It's just the stuff that I'm missing from what's already there. Okay. So, as you can see, I kind of jumped straight to it. I have my common denominator. The things being multiplied times the 4 are just the things that were missing from this term, right? I needed to multiply this times x plus 3, x minus 1. So times 4 is x plus 3, x minus 1. I'm still subtracting 3x. The only thing that was missing here was x minus 1. So that's all I have. Okay. Here, the only thing that I was missing for my common denominator was x plus 2. So I had to multiply that top and bottom. Okay. Once you are familiar with that, it's very nice because you get to, it seems like you get to skip some steps. A lot of students will kind of write an extra line where they write everything they're missing, write everything they're missing, write everything they're missing, and then they combine them with their common denominator after that, and that's fine. Okay, there's nothing wrong with writing more, but you know, I'm taking some liberties here because again, this should be somewhat of a review. You should be somewhat familiar with this material, right? So now that I have this, I could start to cancel things because I have stuff on top. The only problem with that is I do have this times this, right? So whenever I have something in the numerator and denominator, as long as everything's being multiplied, I can start to cancel stuff. So I can cancel x plus 2, x plus 2, x minus 1, x minus 1 if I wanted to, okay? I'm actually going to save that for like the second to third last step. What I'm going to do instead first is I'm going to simplify this stuff because to me, that's more of a headache. So I just want to get it over with, right? So again, the reason being is because this is one term and this is one term. So this is being multiplied against all of this. If I really wanted to, I would take all of this and distribute it across all of that, which I would not want to do, nor would I do. That's a real pain in the butt and super duper unnecessary and not a good time at all. Okay. So again, one of two choices is, since it's this stuff on top and this stuff on bottom and this stuff on top and this stuff on bottom, I could cancel out the things on this side on top with things on this bottom, or I can simplify this first, right? It doesn't matter which order I do, they're both equivalent, okay? So I decide to go ahead and just finish this out since that's what was inside of the parentheses. I just want to kind of knock it out, right? So I expand this term, right? So that's an x squared minus, plus 2x, because 3 minus 1 is a 2x, and then a minus 3. Here the negative 3x distributed across, so you got the minus 3x squared. This minus and minus turns it into a plus, okay? And then this doesn't do anything, so it's x plus 2. Next, I want to distribute this 4 across, or I can cancel this x plus 1, x minus 1 with this x plus 2, x minus 1. But again, I'm in no rush. I'd rather distribute this across. Now that I've multiplied everything in this by 4, right? So 4, 8, minus 12. I can start to now combine like terms. I've already combined one set of like terms just to make things a little bit easier for me. So this should give me a negative 10. Okay, this should give me a 12. And this should give me an x squared. Oh man, what do we have here? The exact same thing. Did I do that on purpose? I probably did. Okay, so this cancels with this because this is in a numerator and this is in a denominator, and everything is being multiplied. So cancel those, cancel the x plus 2 and the x minus 1, and I'm left with 3 over x plus 3. Okay, so now let's talk about complex fractions. So complex fractions occur whenever we have a rational expression inside of another rational expression. Or another way of thinking about that is when you have a fraction inside of a fraction. Okay, we did do an example in the 1.1 video where we talked about decimals and fractions, and how if you divide a whole number by a decimal, we can still turn it into a fraction problem, right? So basically what I did was, it was 8 divided by 1.8. I turned that into a fraction where it was like 8 divided by 40 over 8 or something like that. 40 over 10, I don't remember. 48 over 10, I believe. And then we simplified that. So we had a fraction in the denominator of a larger fraction. So it's the same thing, same sort of problem. Now it's an example of a complex fraction. However, we are going to talk about complex fractions that have rational components, okay? So there's two different ways to do this. We can do one way, which is we simplify it into a single rational expression that looks like this, okay? Or we can do it by what's called clearing the denominator. So the clearing the denominators method is the strongest method that you have probably in an algebra class whenever you have to deal with fractions. And that's the method that I tend to use whenever we have an equation. It does not work for expressions, but it does work for equations, and it does work for complex fractions. It's the method that I prefer to use. It's very, very easy to use once you understand what you're doing. A lot of times I can just look at a problem and get like 3 steps done without having to write anything on my paper. It's very, very, very useful. So I'll show you both ways, and you can use whichever one you want, but I will always be using the clearing denominators method. Okay. So number 1, using arithmetic. Okay, so using arithmetic, we're basically going to simplify the numerator rational expression. So again, the numerator is a fraction and the denominator is a fraction. So we're going to take the rational expression on top and simplify it to a single expression, to a single rational expression. We're going to take the denominator and simplify it to a single rational expression. And then we're going to divide those two rational expressions by multiplying by the reciprocal. Okay. We can do the LCM method, which is we find the LCM of all of the innermost denominators. So all of the denominators of the denominators. Okay. And multiplying the entire rational expression by 1, where the 1 is made up of that LCM over the LCM. Okay, so what this will do is it will simplify it to a single rational expression, which we can then simplify. So we're going to do the same problem twice. We're going to start with the first method. Okay, so here we have 2 over x minus y plus 3 over x plus y divided by 5 over x plus y minus 3 over x squared minus y squared. So again, we have a rational expression in the numerator, a rational expression in the denominator. So what we're going to do is we're going to take this and we're going to simplify it to a single rational expression. We're going to simplify this to a single rational expression. So we'll have a fraction over a fraction, and then we can just divide, right? So we divide by multiplying by the reciprocal of the denominator. So I can start by factoring this. There's nothing else to factor. If there was other stuff to factor, I would factor everything. I can just factor this to x minus y times x plus y. Oh, I guess I didn't. So here, my numerator has a common denominator of x squared minus y squared. I need to multiply the numerator here times x plus y. This numerator times x minus y. Right? 2 times x plus y. 3 times x minus y. The denominator turns into x squared minus y squared. Here, this is x plus y times x minus y. When we factor this, so the only thing that's missing here is x minus y. So I need to multiply this numerator and denominator times x minus y. That gives me a common denominator of x squared minus y squared. And this turns into 5 times x minus y minus 3. Right? So it's almost 1 fraction over 1 fraction. I just need to simplify this numerator and simplify this numerator. So I got 2x and 3x is 5x. 2y minus y is just a y. So this will be 5x plus y over x squared minus y squared. And then this is 5x minus 3. Or minus 5y minus 3. There's not much else I could do that. Okay. So now it's one rational expression over another rational expression. So I will multiply by the reciprocal of this. Okay. So again, this gets flipped. And it goes from division to multiplication. This term and this term get to cancel. And I'm left with this over that. Okay. Very straightforward. Not always the easiest to do. In this case, we didn't choose a super hard complex fraction. There wasn't a whole lot of factoring going on. But sometimes it can get a little messy. It's not my preferred method. Okay, so let's go ahead and look at this using the LCM method. Okay, again, we'll get the same answer because there's only one simplified form of any expression. I already know that the LCM for this is x minus y times x plus y, which is the same as the LCM for this. So again, I'm looking at all of the denominators present in order to find the LCM. It just happens to work that the LCM for either one is the same because, I mean, look, they're both the same, okay? But let's say that I had x minus y, x plus y, and then let's say that this was 2x plus y. I would have an extra 2x plus y here on the top and the bottom, okay? So I'm looking at the common denominator from each single inside fraction, each innermost fraction. So the 4 of these combined, not just the top 2 or the bottom 2. All 4 of the denominators inside of each numerator and denominator, okay? So I'm going to multiply this times this. Now, a really cool thing happens here. If I look at just this term times the LCM, on the bottom I have x minus y. This multiplies across this entire top, just this numerator. So that's 2 over x minus y times x minus y times x plus y. There's an x minus y on the bottom. That cancels with this numerator. So I'm left with 2 times x plus y. Same thing here. The x plus y here cancels with this x plus y, and I'm left with 3 times x minus y. Same thing here. This x plus y cancels with this x plus y in this denominator, and this x squared minus y squared cancels with this entire thing. Okay, because if I multiply that out, I have x squared minus squared. So when I multiply this, I get 2 times this cancels, and this is what's left. So 2x plus y. 3 times x minus y, because the x plus y cancels and x minus y is what's left. Here, if I multiply by both, the x plus y cancels, x minus y stays. On the 3 term, this here cancels with both of these, and I'm left with just 3. And if you notice, I'm left with just a single rational expression. So I kind of jumped straight to this thing. There's just a little bit more math to do. I have to expand this, and I get the exact same thing that I had before. So I prefer the LCM method because once you're comfortable with canceling everything out, right, you just look at your denominator and you say, okay, what stays and what goes? X minus y, well, that goes. The other parts stay. So 2 and x plus y. Here, what stays, what goes with the LCM here? X plus y goes away. X minus y stays. Here, what stays, what goes? X plus y goes. X minus y stays. Here, what stays, what goes? Well, both of them are present, so both of them go away, and I'm left with just the 3. So that's how we work with the LCM method. Okay, so please note that one method tends to be shorter than the other. The LCM method, we had about 3 steps. Okay, this method, we had 1 more step, but in the long run, it's always easier just to kind of clear the fractions out and just deal with the single rational expression than it is to have to add and subtract 2 separate sets of rational expressions to get a new rational expression and then simplify that, right? So please make note of this next section that we're going to talk about right now. This is just common errors that tend to occur as people are going through rational expressions. They're just the same as common errors that happen when you're dealing with fractions, period. Okay, so there's quite a few common errors that people make. So a quick guide: a plus b to any power is not the distribution of that power. So we talked about that in the last video as well. Please note that this is a not equal sign, right? The square root of a plus b, or the nth root of a plus b, does not mean you can distribute this nth root either. Okay, so certain functions do not distribute across addition or subtraction. These two are actually the same rule. So remember, an exponent and a root are pretty much the same thing. The only difference is that a root is a fractional exponent, right? So it makes sense that if one doesn't work, the other does not work as well. Same thing here. You can't distribute this nth root across and say that they both cancel. Okay, that does not work. Here, if you have the nth root of a plus b to the n minus 1th power, that does not reduce it by 1. Okay, so this is a common thing where here people think that they can pull out an a plus b term, and then they're left with one single a plus b, which is true. The problem here is that you are not grouping together the quantity a plus b. This is a value of a plus b times this thing. This is not the value a plus b times the value of this nth root. Okay, so you can pull out 1 to the outside and you're left with a remainder of 1. That is true. However, you have to make sure you specify that a plus b is its own quantity, because this now says a plus b times this. That's different. Okay, 1 over a plus 1 over b is not 1 over a plus b. Remember, you have to make a common denominator. Okay, so you have to make this b over times b over b. You have to multiply this times a over a. A plus b over a, very, very common. I see differential equation students making this mistake. They'll just cancel out the a's here. That does not happen. It has to be a common factor in each term in the numerator. Okay, so you cannot cancel this out and say that it's just b, or cancel this out and say it's 1 plus b. It doesn't work that way. Okay, so those are some common mistakes. Please, please, please try your best to avoid those. They become easier with practice, obviously. And that's it. Okay, I'll see you guys in the next video in section 1.5. Alright guys, see you on the next video.